All right, settled again. I just wanted to comment on the last debate. Kind of follow up on my talk a couple weeks ago. Personally, I don't believe referring to a PCP is going to do you any good for diabetes, because the problem is not, it is not a medical condition in the sense that drugs don't work. And everybody's talking about starting drugs. It is clear from the evidence that drugs do not cure diabetes. They might slow it down if you have bad lifestyle habits, but they don't cure it. And you can at least reverse the symptoms so you don't need medications through lifestyle changes. And I try to make the case that at least with an N of 1 that can be done, but there are many organizations in the country that are reversing and getting people off medications. So I would say, first of all, there's a problem not just optometry, in the medical community in general, that either your PCP or you as optometrist, you say, go do this. And it's important that you do this, and there's absolutely no follow-up ever. That's the way it is with my PCP. Pretty much, Tigers maybe a tad better. But it's generally true. You send out referral letters. Do you follow up, and does the person get back to you so you know you have care? I mean, to me, that's the critical thing. It doesn't do any good to say, I mean, for a lot of years, my PCP has told me to lose weight. You know, I said, okay, that sounds like a great idea, Doc. And then I go off on my own. So you send a letter, or you say, I'm going to refer you to the doctor. Well, did the person go? And if they didn't go, that's what you should do. You can, without any legislation, you can follow up on that. And it's a lot of time consuming, and I think as technology improves, we'll be able to, in the 90s, I wrote my program, Dr. Duke, which did exactly that, followed up electronically. And so I wish I had thought a little bit more commercially. I'd be sitting on the beach in Aruba right now. But anyway, I think at the very minimum, and one other point, as I mentioned before, if their A1C is high, you have waited too long. If their blood sugar is too high, their pancreas is no longer providing enough insulin to counteract the glucose. So the person is already on their way, if not already there with diabetes. And if you diagnose diabetes and seen a problem in the eye, they are really screwed. So you need to get in earlier. And I think as a minimum, just have a lifestyle brochure that says, if you see somebody whose waist to height ratio is looks like they got that little bulge, they're very likely to have metabolic syndrome, and it would be helpful to give them a little brochure about diet and warnings and letting them, suggesting that they go to their primary care doctor. But even today, we talked about managing your diabetes. Nobody said anything about reversing it. And that is going to be true in the next 10 years. The world will be seeing that diabetes can be reversed. But you have to fight the system. You have to fight the system of big pharma. You have to fight the system of big food and sugar and all of that. I mean, and the attack on sleep. So sleep and sugar are your two biggest causes for metabolic syndrome. Lack of sleep. Okay. Let's see, where are we? Are you seeing me? You are. Okay. Today, I wanted to talk about screening was on the agenda. I said, well, what can I do to make screening, I don't know, interesting or not? It's questionable. But I wanted to show you how we go about designing a screening test. And I thought that'd just be kind of informative. And so what we want to do is we want to determine, and my view is the best way to treat myopia is to prevent it. So, in the first place. And so I'm going to develop a couple of screening tests today. I'm going to use the multi-center longitudinal prospective cohort study. It's a big data set. And in this, we're going to look at the first year that the kid enters the study, and we're going to try and predict if he's going to be myopic. Now, we've run the study. We know whether the kid became myopic or not. So we have future emmetropes and we have future myopes. But nobody at that point, we've eliminated anybody that came in the study as myopic. And the purpose of this study was to look at the course of myopia, the development over time. So we're going to do two different tests. One is we're going to look at spherical equivalence at the time the kid came in and at various ages. And we're going to say, given that a person has a particular level of spherical equivalence, can we use that to predict whether they will become myopic in the future? Now remember, they're not myopic yet. And so we want to see, does spherical equivalence predict that? The other thing is we want to look at average time spent outdoors. And is there an amount of time, number of hours that we can use to say you should try and get your child to go outside at least this amount. So those are our challenges for today. So we want to develop cutoffs. So how do we do that? Well, for example, here are the two samples we're going to use. We have a sample. It's the first year in the study. They're not myopic. And we're going to look at kids entering the study at either age 6, 7, or 8. And you can see we had 114 6-year-olds, 376 7-year-olds, 293 8-year-olds in year 1, their first year coming in. And then our sample for outdoors, sample for hours outdoor activity, the way I did this was I looked at people. I only included people from the entire data set who had, I can't remember if it was 2 or 3 years to go before they became myopic. And I wanted to see if they would develop myopia. So we have 7, 8, 9, and 10. Now I end up 9 and 10 appeared to be really too late for doing this. So I'm going to eventually just end up using the 7 and 8-year-olds. Okay, so you're all familiar with linear regression. This is a pretty ugly plot, but basically this is spherical equivalence predicting axial length. It's not exactly a tight curve, but it is a significant relationship. The higher your, as you become more hyperopic, or as you are more hyperopic, your axial length is shorter. And if you're myopic, your axial length is a little longer. But there are a lot of other things going on in here, and that's why all the dots aren't on the line. Well, when we want to develop a cutoff on a question that is binary. So we don't have a nice continuous Y. We have, you're a future myope or you're a future emmetrope, 0, 1. And if you plotted that data out by spherical equivalence, you would get a graph that looks pretty uninteresting like this. Now, what we want to know, what we can do is figure out or look at the probability of an event.
And so we can look at the probability of becoming myopic as time goes on. It has this nice sigmoidal shape. The problem with that shape is that you can't derive a regression equation from it. You need a straight line, and it turns out that this thing called a logit, which is the natural log of the probability of becoming myopic over 1 minus the probability of becoming myopic. Turns out that the logit of this is just like your y equals a plus bx. So the y in this case is a logit. So we have y equals the natural log of p over 1 minus p equals a plus bx. And we can just solve that, and we can get regression coefficients. Now, it turns out, this is just FYI, if you exponentiate the regression equation, you get the odds ratio, the risk that a spherical equivalent, a unit change of its spherical equivalence will increase your risk of myopia, or more an hour extra of outdoor activity will decrease your risk of myopia. And then from this equation, we can solve for the probability of becoming myopia. And the 50-50 cutoff point, which is basically what we're shooting for. We want to say, what is the spherical equivalent that you would need at age 6, where if your spherical equivalence is higher than that, you're going to have less than a 50% chance of becoming myopic. And if your spherical equivalence is lower, or if you're than that cutoff, then you have a certain probability of becoming myopic. So, so we're going to solve for this equation. We plug in 50%. That's our p over 1 minus p. 50.5 over 1 minus 0.5 is a natural log of 1, which is 0. So we just have to solve this equation, a plus bx, and that turns out to be minus a over b. So when we run our logistic regression, we get our intercept and our slope, and we plug in this number, and it gives us the cutoff. So in terms of the spherical equivalence, here are 3 logistic regression equations, each for age 6, 7, and 8. We notice that spherical equivalence is a significant predictor. Your odds change by point. The higher it is, you're more protective, I guess, for each point of each diopter. So it's not, this little number actually gets multiplied by a lot. But it's significant at age 6, at age 7, and age 8. Then if we take minus the constant, which is 0.662, divided by minus 2.04, we get 0.32 diopters. So if you measure your kid, you do your little thing with all your stuff, and their refractive error is 0.32, positive 0.3, they're emmetropes, basically. If they are 0.32 at age 6, then that's the 50%. If their diopters are more than that, they're not likely to become myopic, or they're less likely to become myopic. If they're less than that, they're more likely to become myopic. So you can get a hint when you have your kid in your chair. If they're a 0.32, it's not, oh, he's fine. No, not necessarily. And this is the cutoff based on this longitudinal study. At 6, at 7, it's actually a little higher. I was looking for a nice systematic drop, but didn't get it. Anyway, so about a half diopter. If you're 7 years old and you have a half a diopter of positive plus 0.47, you're emmetropic in the 0.47 area, you have a better than 50% chance, if you're less than that, of becoming myopic. And by 8, you got to be closer. It's a little bit closer, 0.04. So if you're almost perfectly emmetropic, 20/20 at 8 years old, then there's a good chance, or there's some chance, an increased risk, that you're going to become myopic. Okay, now I want to kind of, I'm not sure if we covered this before, but I just want to remind you that we're going to have the condition of truth, which is they are a future myope. And then our test condition, are you less than 0.32, or are you less than that cutoff? And if so, then, and you are a future myope, then you are a true positive. You're going to become, this is the number of people that went on to become myopic, who at 6, 7, or 8 met that criteria. The same way with true negative, if your test outcome is you're greater than that cutoff, and you actually become a future myope or a future emmetrope, then you have your true negatives, and then the off things. Now, I want to remind you that there is sensitivity and specificity, and when you're reading the literature and stuff, those are the numbers that are most often talked about, because they're the easiest ones for a person doing the study to get. But a sensitivity means if you have a person in your chair and they are in fact and you know they are myopic, then you do the test to see whether they're myopic or not. And the sensitivity says if the test is positive, they're myopic. If the test is negative, they're not. But that's of little use to you if you already know they're myopic. So sensitivity is the quality of the test under a known condition. And you are really more interested in positive predictive value. And that's going this way across here. So if the test is positive, this gives you the probability that they are actually going to become myopic. And for negative, if the test is negative, then this is the probability that they will actually stay emmetropic. So that you don't know, I mean, what's the point of doing a test if you already know the answer? You know, just statistical sanctification, I call that. I mean, the difference is obvious. You know that it's there, but I'm just going to give this value, do this test anyway, just to sanctify the results of what I already know. Now, that's silly. So in this particular type of study design, where we looked at everybody at the beginning and followed them along, we don't really put people in, just select a bunch of future myopes and a bunch of future emmetropes and look at the data. We just follow and determine how many people are one way or the other. And so let's see how well we did. So at age, here's the chart for age 6 years old. And this is, I calculated the probability. I used that little formula. P equals the exponentiating the model over 1 plus exponentiating the model. And I got this predicted each person's, this isn't the actual, this isn't the observable data, this is the predicted model. And then I calculated, that's the 0.32 diopters. Here's 0, myopia is down here someplace. There were 11 people that, down here, they were a future myope. The screening said they would be a future myope, and they in fact were a future myope. So there's 11 of those. There were 72 who I said would be emmetropic, and they actually were emmetropic. And there were 5 who I said would be myopic, but I was wrong. And there are, or no, 5 I said would be emmetrope, and I was wrong. And 26 I said would be myopic, and I was wrong. And so in this case, the specificity, the ability, if we know the answer, the ability to correctly predict that you don't have the problem. So that's 94%. That's really good. The sensitivity was 30%. So if I know the person in my chair is myopic, then my test is 30%, is able to pick out 30% of those people. That's not so good. But the positive and negative predictive values, which is a point to show you sensitivity and specificity are not the same. So this is sensitivity at 30%, but positive predictive value. That is, if they get a positive test, then a positive in the sense that you have myopia, or we're predicting you do, then it was 69% correct. Negative predictive value was 73%. These are the numbers you care about. So if that person comes in and they're under 32, you have a 0.69 chance that, or the probability of them becoming a future myope is 0.69. So they have that. And if you say they're not, then that's about 73%. At age 7, it's similar in our positive and negative predictive values. Our specificity is going down a little bit. Our sensitivity is going up a little bit. And we have this really nice looking, sort of nice looking sigmoidal curve. So, you know, not too bad. At 8 years old, we're starting to lose our sigmoidal shape. If we had it's kind of getting up here close to the point where really it's going to, down here, this is -1. So we're about to see a bunch of myopes, which are going to flatten out the top of this. But that was 0.04 diopters. Again, the negative was 87, and we had a winner at 0.73. And our sensitivity is really bad at this point. All right. So, oh, shoot. I forgot to set my... So anybody have any questions about that? What do you think? Did you guys, I'm sure in your classes, you talked about the fact that a kid comes in and sits down on your chair, you measure him, he's emmetropic, but you say he's going to become myopic. Did anybody give you any criteria? What do they say? What is your criteria? About a half a diopter? Yeah, if you're 7, that would be a good one. Yeah. So, yeah, it's an interesting thing. And if you get too old, it's probably not a half a diopter. It's got to be a lot closer. Because your eye's growing and it's reaching its point. Reaching its point of emmetropization, and it has to be really further along. All right. Now let's look at outdoor activity. Now, a lot of times in the literature you see case control studies where people pick a bunch of myopes and a bunch of emmetropes, and then they look to see what caused that. Well, I did a similar thing with the same data set, and I did a propensity analysis. And a propensity analysis says, let's match our future myopes and our future emmetropes. Let's take a subset of the data and get people to match. Because, you know, at the beginning, if their spherical equivalences are different and all sorts of, and everything's all different, then you're really not doing a fair test of outdoor activity. So what I wanted to do was make, at the point of starting this, when they were still 2 years, at least 2 years to go before they became myopic, I wanted to age match. I did this separately for each age group. And I wanted to match on spherical equivalence, axial length, peripheral refraction, just everything. And there was a zillion different parameters, and matched on a bunch of them, say, not a zillion, but maybe 10 or 20. And what you do is you predict so your outcome measure, in your logistic regression, and this is the matching part, not the testing part. We don't use any kind of activity measure included in this, just all eye characteristics. And then we say, what is the probability, given that you are a future myope or you are a future emmetrope, what's the probability, given all these parameters, that you will be a future myope or a future emmetrope? So let's say you're 0.7 that you're going to be a future myope. Well, if you are in fact a future myope, then 0.7 is, that's the probability you're going to be there. But the thing is that our little, using all these eye characteristics, are not perfect. So somebody who's going to be a future emmetrope is also going to have a probability of 0.7 to be a future myope. So we match those two patients on their probability of being a future myope. So that's 0.7. Some people have a 0.3 of being a future myope. We find a myope who was predicted to be an emmetrope, and we find an emmetrope that's predicted to be an emmetrope with 0.3. And we match all of these. And we were able to make 200 and some odd pairs of matched pairs. This is I call this case control study on steroids, because when you do a normal case control, you try and match them, but you don't do anything very formal. This is a very formal match between those two. Now, this is a chart. This is a chart of the probability of becoming myopic. This is the predicted probability, and this is the proportion of time. Okay, so in this study, they asked parents to say how many hours a week does your child study? How many hours a week on the computer, reading, watching TV, going outside? And if you add all those activities up, the range that the parents gave in this study was 4 hours of doing all that stuff. I don't know what they're doing if they're not doing that. They're just staring at the wall. But it went from 4 hours to like 120. I don't remember what the number was, but it was up in that neighborhood. So they were bad at estimating quantity of time. So in this case, I'm going to kind of make the assumption, okay, you don't know how much actual hours. You had trouble doing that. And maybe they were thinking of just for the 4 hours, just one day. One day, how do I split that up? But I just guessed, okay, you can say my kid spends X proportion of the time studying, reading, computer, TV, and outdoors. And then I took the average number of hours, which the average of everybody was that a kid outside of school and on the weekends has 20 hours, which 26, I think it was, which is also really small. So then I did it both ways. I split the difference between the range. I took the mid-range, which was around 50 hours. And so I did a sensitivity now. So I looked at it both ways, at 26 and 50. But here is the cutoff using the proportion. In terms of the proportion of time spent outdoors, that's the 50% level. If you spend more than 28% of your time, free time, when you could be reading, studying, computer, TV, outdoors, 28% of that time was devoted to being outside. That was kind of another thing. They said sports activity. They should have just said outdoors. But in all fairness, they were the first people to even look at this. So other people later on have just focused more on outdoor rather than sports. But So if you're more than 28%, you have a smaller chance of becoming myopic. And notice that it's significant. So, in fact, we could predict future myopes based on, so this is a different logistic regression. Now we've got our matched pairs, and we're looking at number of sports, number of the proportion of time spent outside, and we're predicting whether or not you're going to be a future myope. So that's that 28% of the time you're out there, you're doing more. Now, I'm not going to go into this too much, but basically in a case-controlled design where you're fixing the number of people in each group. So we did matched pairs, so we forced the number of people to be the same. The number of people isn't the same in the real world. It's like in this particular sample, it's like 31% of the time people were myopic of the whole sample. But we forced a sample that was 50-50. So when you calculate positive predictive value, you can't do it the same way as we did for spherical equivalence, where there was no restriction on the sample. So there's Bayes' rule, and Bayes' rule gives you this nice little formula that involves prevalence. And we know, to calculate, it's like sensitivity times prevalence over, well, this is the formula. And prevalence in this case was 31% of the people became myopic. And so, so that's the formula. Negative predictive value has a similar thing. And, you know, I think, I know you're talking to Citic this semester. Has he talked about his nystagmus? Oh yeah, it's the end. He must have talked about nystagmus and drunk people. Yes. Okay. So in his study, so he teaches the officers to do it. Well, prevalence really impacts on the effectiveness of this test. So if the officer is watching the road and somebody is kind of weaving around, he just assumes or makes the assumption that that person could be drunk. They're either sleepy or drunk. He'll pull them over and he'll do his little test. And it turns out that the prevalence of an officer getting it right is about 70%. And when you plug in 70% to the formula on his nystagmus test, you get a pretty good positive predictive value. If they are drunk, you're going to be right most, really, I don't remember what it is, but say 90% of the time. Then there's another kind of stop where there's a roadblock and they stop and test everybody. And the prevalence there is about 7% of the people stopped at a roadblock are actually drunk. And if you use this test there, and you relied only on that test, you would send about 80% of the people to jail wrongfully. You'd be wrong 80% of the time that you said they had a problem. So prevalence is very important. And so if we were doing this study in China, our prevalence would be closer to 80-90%. We did it here a number of years ago. The prevalence was 31%. So it matters in terms of your probability of being correct if you pass the test. And so you can see here we had 258 people in each group. We have specificity and sensitivity, which sensitivity at 61%. So I wouldn't say it's like a coin flip as to whether you have it, because the prevalence is really only 31%. So it's a lot better than a coin flip. But this is if you know what the future is. If we plug in our value, the positive predictive value is 0.368. Now remember, the prevalence is 31%. And we're plugging our formula in based on our test, our cutoff of 28% of the time, being above or below that cutoff. We're just boosting it, really, probability of guessing at 31% up to 36. And the sensitivity or specificity, the negative predictive value, is 0.31. So even though sports activity or outdoor activity, everybody says, this is outdoor activity is really important. It does have a significant, statistically above chance at 0.001, but it's actually not all that great. So unfortunately, I can't tell you to advise your kids to, spend 28% of their time, more than 28% of the time. Now, the more over that they do, their chances of becoming myopic are reduced. It's just not as good as we would like. Okay. One more note, and this is completely different. Forget myopia. Well, actually, not completely forgetting myopia, but one more little thing. And this was a suggestion of one of my past graduate students, and also a student here, OD student here. And we're going to be doing a study on this. But I think this is a marketing suggestion for you to take out when you go to your new practice. Something you can do to drum up some business. And that is this simple little test where you put your hand over your eye, and it's a poster. Think of it as a poster. So you tell the person, put your hand over your eye, your right eye, and look at the poster. Now put your hand over the other eye. Do you see the poster as well? And you guys try it. Do you see the same out of both your eyes? And if you don't, then there's a problem. I can tell you that I think it's been 5 years, I've worked here 12, and I think after about somewhere between 5 and 6 years ago, I learned for the first time in my life that I'm not looking at you out of my left eye. I suppress it. I'm amblyopic, and it was a complete shock to me. I was wearing flicker glasses. I went in the bathroom. I couldn't see my left eye, and I said, "Oh, that's weird. Is that flicker not working there?" And I covered my right eye, and there was my left eye. I said, "I'll be darned." And so people don't know what they don't know. And so you have this poster up there to tell them to go. Now, you guys know you got a problem if you do, but people like normal common man in the street doesn't know that what he doesn't know. So we're going to test this. Any of you doing an internal rotation next year, if in the clinic somebody says we're going to hand these out and we're going to hand out the posters, we're going to ask people to take the test, and then we're going to use the results from your exam to determine if the test, how well the test predicted a problem, how many it missed, how many it got right, do sensitivity, specificity. And then so when you graduate, you can ask, does the screening test work? Because I'd really like to do it and make millions of dollars with a flood of patients coming into me as a result of this. So that's it. So congrats on getting through your classes. Enjoy your new adventures. It's been a pleasure working with you, and have a good life.
I bet you these guys can tell you how many patients they've had come in that they do their occluder and they occlude one eye and then they occlude the other eye, and the patient looks at them and says, "Oh my God, I've never noticed that before."
Yeah.
Is that okay?